Greetings and welcome to a new video about electric circuits. In this example I will discuss a very important theorem which is called the Extra Element Theorem, developed by Professor Middlebrook from Caltech. And this theorem is very important and very useful if you want to develop or present your transfer function in a very nice way where you see the poles and the zeros directly. In this case we will specifically use that to determine the transfer function for an RC circuit. It can be also applied for other circuit analysis. Of course, we can use the standard theorems, the standard methods to determine transfer function that will be also discussed in this example to compare actually the two methods. Unfortunately, this method, the extra element theorem, is not really discussed much in electric circuits books. So if you want to find this, it is really hard to find. So that's a kind of a pity, but I will try to help you guys also using these videos. I will do more videos about other circuits and other topologies, and we will see how we can apply that here in this RC circuit. So let's go and start right away with our objective. So we would like to use this extra element theorem, short for EET, and determine the transfer function A, which is given by VO over VI. In this case we have the simple RC circuit where you see two resistors, one capacitor, so input and the output nodes here. The transfer function we like to know A can be then determined using this extra element theorem using this formula. We have actually here several parameters. We will of course discuss that shortly step by step. You see here the A, which is defined for a specific impedance which is going to infinite, and we have here Z, which is our, we will see that shortly, our extra element. We have here the Zn, which is our nulling impedance, and Zd, which is our driving point impedance. So there are several elements we need to determine. That will be done shortly, and we will see that step by step. And here we will designate the capacitor C as our extra element. It doesn't have to be our capacitor, it can be also the resistors R1 or R2, it doesn't matter, but you have to select the element, one of the elements here in the circuit. In this case we will select that as the capacitor C. And the C here has an impedance, we know that from AC circuits, 1 over SC in the Laplace domain. Okay, so let's see that using the extra element theorem. Step 1, what do? Now we remove our capacitor C from our circuit and we calculate our voltage gain. And that is actually this voltage gain here, designation here. So that's the capacitor that's gone. The rest is actually in the circuit still. So the input voltage R1 and R2, and we measure here actually the output voltage, and we do the ratio, which is our voltage gain. So the VO over VI, which is then the voltage divider here, R2 over R1 plus R2, that is now defined as the impedance, I mean the gain for a specific impedance, which is then the extra element opened. That's step 1. Step 2 is disable your input. In this case it is a voltage source, so that means input source will be then shorted. And then determine the driving point impedance Zd between the capacitor nodes. In this case that means the following. So the input is disabled, that means shorted. It can be also a current source, that means that it should be then opened. Then we will look again between the two nodes here, which is called now Zd. Now what do we see? Well, we see here between these two nodes, meaning actually these two nodes, that the R1 and R2 are effectively parallel, because this goes through resistor R1 to this node, which is ground, which is also the same for R2. So Zd is R1 in parallel with R2, and that's also given by this formula, so the product divided by the sum of these two resistors. Okay, that was step 2. Now step 3 is null the output node, meaning make this 0 volts, doesn't mean make this short, and then determine the nulling impedance Zn, looking again between the two nodes of this capacitor, what we call the extra element. Okay, let's bring up our circuit. Again, the VI is here back in the picture, so that's not shorted. Here we see the Zn we would like to determine, and this is now 0 potential here. So this is 0 potential, but this is already ground in this case, so that means the voltage between these two nodes is 0. So 0 minus 0 is 0. That means looking here between these two nodes, we actually see a voltage 0 divided by some, let's say, current, which is always 0. That means our impedance Zn will be then also 0. So in this case we have an Zn, which is our nulling impedance, is 0. So we have now all the elements for our formula, which is now this transfer function. We found this here from step 1. ZD we found actually in step 2. Zn we found in step 3. And Z we know that that is our extra element. That is our 1 over the SC. So we can now apply the extra element theorem and we can substitute here that in this formula. So here we go. That's what we do. So we have now R2 over R1 plus R2 times this 1 plus, now we have here 1 over Z times Zn format. That's actually what you see here. So 1 over Z is actually SC, that's what you see here, times 0, that's from Zn, from third step. The similar case is also here, so 1 over Z times ZD, you can actually write it down also in that form. That's what you see here, so C, SC, times the parallel combination of R1 and R2. Now, since this is of course 0, we can also write it like so. So this is our transfer function. As said before, you can recognize here directly that we do not have a 0 here, but we do have a pole, which is then given by setting this equal to 0. So that is actually pretty nice. But of course, it can be also done in a more familiar way. We know that from circuits, and that is done using the standard circuit analysis. That's actually what we now do, compare now the results. So let's do that. So we will create first a parallel impedance that's formed by R2 and C. So that's actually called here ZP. So ZP is the parallel combination of R2 and the impedance here for capacitor C. That's 1 over SC, and we do that product divided by the sum, and we will work it out, and we will get R2 over 1 plus SC R2. Now we will now apply the voltage divider rule, as we have done it also for the other cases, and then we will determine the voltage gain. So that means then ZP over R1 plus ZP. So we know that ZP is this one, which is from step 1. And we can apply that here, and we substitute that, and we also multiply the numerator and denominator by 1 plus SCR2, and that's shown here. We can also work out this parenthesis here, because that's R1 times this one and R1 times this. And you take the R1 and R2 together, and you have this expression. Next, in order to compare that to the form we had from extra element theorem, we can now divide actually the denominator by R1 plus R2. That's actually what you see here, so you can take it out. You also need to do that for here, and you also take out this R2 here out of the numerator. You actually have this term in front of it. Okay, now we have this form, and you can see here the R1 times R2 divided by R1 plus R2, which is actually the parallel combination of R1 and R2. We already determined that in step 2 using the extra element theorem. So this is now the expression using the standard circuit analysis, and this was the expression we have determined using the extra element theorem. Now you see actually they are exactly the same. So these are very nice results where you see directly that using the standard circuit analysis we get this, and using the extra element theorem you get that. You might say, well, this method is much faster and also more intuitive than this method where you actually have a couple of steps and maybe not really handy, maybe also overkill in this case. Well, it might be true in this simple example, but if you have a very complicated circuit, then you really prefer to use this extra element theorem. And I will show you that next video. So stay tuned for a next video about the extra element theorem where we discuss more complicated circuits. So see you next time in another video. Take care.